Hi, everybody. I'm going to go over a little bit about hydrolysis reactions in the next couple of videos. So this video, I'm going to focus on acidic hydrolysis. So we're starting to go into the realm of more in the carboxylic acid derivatives. So we've kind of talked a little bit about, aldehydes and ketones and their reaction with weaker nucleophiles. Now we're going to start talking about what happens when we use a weaker nucleophile or other kind of nucleophiles besides the Grignards, which we've already seen. But what happens when we use those other types of nucleophiles for these types of carbonyls? So acid chlorides, anhydrides, esters, amides, nitriles, those all kind of fall into that realm of carboxylic acid derivatives. The one kind of outlier is probably the nitrile, because you can change all of these, so you can get all of them from a carboxylic acid. A nitrile, a little bit harder to get from a carboxylic acid, but they're still kind of grouped in the same realm because we still have a carbon that has 3 bonds to a heteroatom, so it still has the same oxidation state as, something like an amide or an ester, and has similar reactivity. So we're going to group that one in as well. So the important thing to know about all of these types of carbonyls is that if you have acidic or basic conditions, you can hydrolyze them to the carboxylic acid. So essentially all roads lead to carboxylic acid if you have one of these as starting materials. So it's a really handy thing to know that we can always get back to this. And pretty much once you have this carboxylic acid, you can get to any of these, not the nitrile, but or at least not that we'll be talking about. So it's definitely a really handy intermediate to kind of have in your back pocket. So we're going to go through the acidic hydrolysis here, and in another video I'll go over the basic hydrolysis. Alrighty, so the first thing, we're just going to start with the acid chlorides. I'm going to go left to right here, and we're going to do the mechanisms. And hopefully by the time we get to the end, you'll see that they are very, very similar mechanistically, which is why I grouped all the acid ones together. Okay, so we've got acid and water. I'm gonna try to keep track of my arrows as I go in terms of whether or not I have equilibrium or not. And we'll kind of talk about what's going on with those throughout. So for the acidic ones, we have a lot of equilibrium. For the basic ones, we will have some less. So we'll talk about that when we get there. Okay, so first thing, I've got acid. I need to protonate my carbonyl. Must. Okay, so now I've got a protonated carbonyl. It's a really good electrophile. And then I'm going to use water as my nucleophile. And hopefully this is kind of bringing to mind the various like acetal, imine, hydrolysis stuff that we talked about, because it is very heavily related. Okay, so I can go through this intermediate. I can go ahead and have water deprotonate that to get to a neutral structure. Okay, so now I'm pretty much at a tetrahedral intermediate. We know what to do with those. We want to do reform a carbonyl and kick off a leaving group. Okay, so the important thing to keep in mind with all these carboxylic acid derivative reactions, they go through what's called a nucleophilic acyl substitution mechanism. And that is just substituting out something on an acyl group. So acyl means a carbonyl, and we're just substituting one of the things on the carbonyl for something else. So that's all that's happening here. It's not more complicated than that. Okay, so I've kicked off Cl- as my leaving group. I've got a protonated carboxylic acid here, so then I just need to go ahead and use water as my base, deprotonate that. and I'm at my final product. And I've actually regenerated my acid catalyst. So this is a catalytic process. Okay, that's acid chloride, that's it. So it should remind you very, very much of the acetal, amine, enamine hydrolysis reactions that we've seen mechanistically, because it's very, very heavily related to those. Okay, let's go ahead and move to anhydrides. So this is the acid chloride. And hopefully you'll see a few of these and you'll start to pick up the pattern. And that's kind of the point of this. Okay, so I've got my carbonyl. We're going to go ahead and protonate that. So in the case of the anhydride, I obviously have two carbonyls that I could choose. There's not going to be a lot of preference because they have resonance between them. So not really helpful in that respect. I will say we're probably going to do not so much with anhydrides as with the other ones, just because they're not quite as heavily used as some other carboxylic acid derivatives. So we're not going to spend much time on them, but just want to have it in here so that you've seen it once, at least if it comes up somewhere else. Okay, so pretty much all the same steps that I've already done before. Now we're ready to deprotonate to get to a neutral compound. Okay, so I'm at this point. Now I need to have my leaving group kick off. So I can have a lone pair form a carbonyl. This whole piece is going to be my leaving group. So this is actually a better electrophile than an ester because this leaving group has resonance. So it's a resonance stabilized leaving group. So it's a much more stable in terms of leaving group ability, which makes it a better reaction. Okay, so then I've got this O minus. It's probably going to go ahead and get protonated. I probably should have. Well, no, I mean, this is a pretty stable conjugate base, so I'm not too worried about that. All right, so then we've got water is going to come in, protonate there, or deprotonate to get to my carboxylic acid. All right, let's do an ester. All right, same thing. We're going to start by protonating the carbonyl. Okay, so now that we've got it protonated, I'm going to go ahead and move this down so I'm starting to run into things. Then we're ready to have water come in to do its nucleophilic attack. So we're going to attack there, push electrons up, just like our other carbonyl reactions. Okay, we get to our charged intermediate. Go ahead and deprotonate that with our base. Okay, we're ready for our substitution part. So we're going to have carbonyl form, leaving group leaves. Okay, so in this case, I'm not a huge fan of the leaving group that I just drew out, because that's an O minus when I've got, and it's, you know, a fairly basic one. We talked about how this is a pretty bad base because this pK is about like 5, so it's a pretty poor base. So depending on what kind of acid you have around, it may or may not be protonated. This though, it's not that great. This one has a pK of about 16, so it's a pretty big difference here. So what we should do instead, if we find ourselves running into that position where we're trying to kick off a leaving group that looks like it should not belong in acidic conditions, we should just protonate it ahead. So I'm going to do a little bit of erasing here. Let's erase that. Okay, so instead of kicking that off right now, let's go ahead and protonate this oxygen first. Okay, so now we have it set up to be a nice leaving group. Because once it leaves, it's going to be neutral. Okay, so we formed an alcohol in this process, and then we can go back, have our water come in, deprotonate that, and we get to our final carboxylic acid. Okay, so we end up giving a good leaving group so that we're not ending up breaking any rules along the way. Okay, never a bad thing when you draw a mechanism to kind of look at it and go, maybe that doesn't work out so well. And we could protonate this ahead of time too. That's totally fine. You know, you can even use this to protonate that, to deprotonate that. There's a lot of options. I'm less worried about this one just because this is a much more stable negative charge than this one is. So it's not that bad to have that one as a negative in my opinion. Okay, so now we're on to the amide. So this was our ester. Okay, so we're going to have our amide. Okay, same thing here. First off, we're going to start by protonating the carbonyl. And hopefully by the time you get to the end of this video, you're drawing along with me and going, oh yeah, I know what's going to happen next. Okay, so now we're ready for the attack by water, the real hydrolysis part here. Okay, so then we end up here where we need to deprotonate first. So we can bring in our water here, grab one of those H's, nice little acid base reaction. And then we end up at this intermediate. So just like I ended up before, I have a very similar situation with these two. So what we want to do is protonate this ahead of time so that we don't end up making an N-, which is really basic. Okay, so we're going to start by protonating our nitrogen. And again, very similar process to what we saw in the acetal hydrolysis, where we had to do a lot of protonation, deprotonation before we were ready to, you know, finally kick things off. Okay, so now it's set up to be a good leaving group. So now we can have our carbonyl reform, kick off the amine. So I'll move this over a touch. Okay, so I can have my protonated carboxylic acid. I'm also going to form dimethylamine here. Okay, so I've got dimethylamine. That's a fairly good base. It's got a pK of about 9. So it's not like super basic, but it's more basic than water as a base, because the pKa of water when it's being a base, so the acid of that would be about like -1. So this pKa is about, well, actually, let me put it on the conjugate acid. That'll make more sense. So if we have that amine formed, that's actually going to be our base now. And so what that's going to end up doing is, once we do this, that's actually going to be an irreversible step. So when we get here, this pKa of the ammonium is about 9, and the pKa of the protonated carboxylic acid is about -7. Okay, so we have a very, very large preference for that side of the equilibrium where we've got the positive charge on the nitrogen. So pKa of 9 versus pKa -7, this is going to be irreversible. Okay, we're going to have an overwhelming majority in that product side. Okay. All right, let's see the nitrile. All right, so first things first, we're going to protonate. We have to think a little bit more about what we're going to protonate. It's still going to be the atom with the lone pair, so it's going to be our nitrogen in this case. And it looks insane when you first start drawing it out, but I promise it's going to get better. Okay, then we can have our water come in and attack. Okay, so then we end up here. So we're already at a neutral intermediate, which is kind of interesting. Oh, actually, we're not. I lied. That's only because I drew it wrong. There we go. Okay, so now we can go through and do the same thing. We're going to deprotonate first. Okay, so now we're here. So this is kind of an interesting situation where we essentially have all the pieces ready for an amide. We've got an oxygen, we've got a nitrogen, we've got a pi bond, like everything is kind of pointing in the direction of amide, and that's exactly what it's going to do. So if we look at this resonance structure, and keep in mind this is a resonance structure, not any like reaction happening. So I'm going to make sure I use my resonance arrows. Okay, then we get to this resonance structure. Now you can start to see it a little bit more, where we've got the oxygen carbon double bond, nitrogen over there. So we're essentially going to do a tautomerization to the amide. So there's a couple things I need to do. I need to protonate my nitrogen. Since I'm an acid, that's going to be the first thing I do. Okay, and then I just need to go ahead and deprotonate my oxygen. I'm going to turn this now so that it looks like we'd expect. And then we have our amide. So we are still in a reactive form right now. So this amide is going to happen just like this one did, where we're going to go through those steps to hydrolyze that amide to the carboxylic acid. Okay, so we've got acid. So we're going to go ahead and protonate carbonyl. Then we're ready for our water to come in and attack. Okay, we can do a proton transfer. So we're going to use water as a base to go deprotonate the oxygen. Then I need to make sure that my nitrogen, my amine, is going to be a good leaving group. So we're going to go ahead and protonate that ahead of time so that it is. Now we're ready to go ahead and reform our carbonyl. Kick off our leaving group. Okay, I've got, again, a same kind of pKa difference situation here where my amine is going to be a pretty good base. We're going to go ahead and deprotonate that carboxylic acid. That step is going to be irreversible. And we're going to form ammonium. Oops. As byproduct. Okay, so all of them, we get to the same carboxylic acid at the end of the day. So I'm going to go ahead and do the basic video. So make sure you watch that as well, because you can do acid and base. So hopefully this was helpful, and we will keep talking about this for a little bit. Have a good one.